Ratnamala, Assistant Professor of Physics, V.V. Vanni Perumal College for Women, Virudhunagar. Today, in this module, I am going to explain the details behind dielectric materials. Here is the objective of this module. First, dielectric materials, then polarization, then frequency and temperature effects on polarization. Next, let me derive an expression for internal field, then Clausis Mosotti relation. First, let me explain dielectric materials. What is dielectric materials? All we know that dielectric material is a insulator. Yes, it is a poor conductor of electricity, but it is a very good supporter of electrostatic fields. So we can use it to store electric charges. Therefore, it having high specific resistance and negative temperature coefficient of resistance. Then, the electric charge within the dielectric material remains fixed in the region of particular applications, whereas in the case of conducting materials, the stored charge immediately spread over the surface. Apart from this, dielectric materials having dipole moment. Yes, electric dipole moment permanently or temporarily when we apply field to that material. So therefore, the dielectric material is an electrical insulator. But all the dielectric insulators need not be the dielectric one. For example, vacuum is a pure insulator, but it is not a dielectric one. Here comes the examples for dielectric material: glass, mica, paraffin wax, etc. So clearly we say that the dielectric materials having dipole moment permanently or temporarily by applying electric field to that material. Here comes the difference between dielectric material versus insulating materials. The materials that can develop an electric field with minimum loss of energy is referred to as dielectric material, whereas insulating material have low conductivity. So therefore, it obstructs the flow of current within a material. And dielectric material have some weakly bonded as compared to insulators, whereas insulators having some heavy covalent bonded within each other. Next, dielectric material lies their application in power cables, capacitors and many more. Whereas in the case of insulating materials, we have used these materials for high voltage systems as well as conducting wires. Next comes polarization. In the dielectric material, always most of the electrons are bound to the parent nucleus. So by the application of external field to that materials, the electrons are displaced from their original position. So therefore, the centroid of the electronic cloud is separated from the centroid of the nucleus. So at that time what happens? Yes, an electric dipole is created at that point. So therefore, we can say that the atom is a polarized one. This particular phenomena is referred to as polarization. So by the application of electric field to the dielectric material, polarization occurs. So here is the diagram. In the absence of electric field, the atom is in unpolarized manner. But after applying field to that material, the atom gets polarized. Here the dipole is produced within the atom. So this particular process is referred to as electrical polarization. Moreover, the polarization is the component of four terms: electrical polarization, ionic polarization, space charge polarization, then orientational polarization. Just now we came across by the application of electric field, polarization occurs. The occurred polarization depends on the time. Yes, next let me explain polar and unpolar molecules. Polar molecule is nothing but the center of gravity of positive charges doesn't coincide with the center of gravity of negative charges. Such type of molecule is referred to as polar molecules. So therefore, polar molecules having no dipole moment. Here is the example for that polar dielectric molecules: water, carbon dioxide, ammonia, hydrochloric acid, etc. Whereas in the case of nonpolar molecules, the center of gravity of positive and negative charges coincides with each other. So therefore we can say that nonpolar dielectric molecules having permanent dipole moment. All the diatomic molecules belong to this category. Some more examples are shown here: H2, N2, O2, etc. As we have already said that polarization mechanism is the components of four terms: electronic polarization, ionic polarization, orientational polarization, then space charge polarization. Such polarization occurs as a function of time. Hence, let me explain the frequency and temperature effects on polarization. So, here is the diagram which shows the frequency effects on polarization. Here we see that the electronic polarization occurs at all frequency ranges. Therefore, this kind of polarization is an instant process. This occurs at all frequency ranges. Next, ionic polarization. Ionic polarization is the slower process as compared to electronic polarization. It occurs only at optical and visible frequencies. It occurs only at optical and visible frequencies. The third one is the orientational polarization. It is the slower process as compared to the previous two processes. So therefore, this kind of polarization occurs only in electrical frequency region. The fourth comes space charge polarization. It is the very slowest process as compared to all other. So therefore, the space charge polarization occurs only at power frequency region. As we have already said that electronic polarization is a rapid process. So therefore, the frequency of the voltage is very high in the optical region. Therefore, it occurs at all frequency ranges. Next, ionic polarization. It is the slower process. Therefore, here the ions do not respond at all when the voltage corresponds to only visible and optical frequency region. The third comes orientational polarization. It is the slower process than ionic polarization. It occurs only at electrical frequencies which are smaller than the infrared frequency region. Finally, space charge polarization. It is the slowest process and it occurs only in power frequency range. Therefore, we can conclude that thus at low frequencies, the value of total polarization, that is electronic, ionic, orientational and the space charge polarization value is very high. Whereas at high frequencies, that is in the region of optical frequency, the value of total polarization is very small. Next, let me explain the derivation for local field or internal field. It is nothing but the space or the average time required to find an electric field intensity at the particular point. For this, first let us consider the dielectric material, and the dielectric material is inserted between the plates of parallel plate capacitor. Now we are going to apply the electric field to that dielectric material. Our aim is to find the electric field. That particular field is referred to as local field. It is the components of four terms: E1, E2, E3 and E4. Let us find one by one. First, to find the field E1. E1 is the electric field intensity at the point A due to charge density on the plates. Yes, due to charge density accumulated on the plates. Here, we write the formula for the electric field intensity E1 equal to D by epsilon naught. D is the electric displacement vector, whereas epsilon naught is the permittivity of the free space. We know that the electric displacement vector is the combination of epsilon naught E plus P. Here E is the electric field, applied electric field, and P is the polarization vector. Yes, dipole moment per unit volume. Substitute the value of electric displacement vector in the field intensity E1. We get the answer E1 equal to E plus P by 3 epsilon naught. Next, let us find the field E2. E2 is the field intensity at A due to the charge density induced on both sides of the dielectric material. So, therefore, E2 is equal to minus P by epsilon naught. Hence, next find the field E3. E3 is the field intensity at the point A due to atoms contained in the spherical cavity. Due to the atoms contained in the spherical cavity. Here we are assuming that the structure inside the material is a cubic one. So, therefore, the field inside the atoms is 0. So, E3 is equal to 0. Next, let us find the field E4. This is nothing but the electric field intensity due to the polarized charges on the spherical cavity. Here it having some 4 parts. The first one is that, let us consider the spherical cavity. Within the spherical cavity, let us assume the circular ring, the elementary circular ring having area dA, and the area is subtended between the angles theta and theta plus t theta. Here theta represents the direction of the applied field. So, first let us consider the spherical cavity. Within the spherical cavity, let us assume an elementary ring having area dA, and the area is subtended between the angles theta and theta plus t theta. Let us find the area dA. So, dA is equal to 2 pi r squared sin theta t theta. Here is the second step. In the second step, we are going to calculate the total charge present on the surface area. Consider surface area dA. It is nothing but the product of normal component of polarization and the surface area. We have already derived the surface area. Substitute the value, we get the total charge accumulated on the surface of the plate. dq is equal to P cos theta. Here P cos theta is the polarization. P cos theta into dA. We have just derived the value of dA. Substitute the values. Next, the third part. The third one is that we have to find the change in field intensity. Yes, it is represented by the letter dE4. dE4 is equal to dQ by 4 pi epsilon naught r squared. We are having two components. Yes, cos theta and sin theta. Here in this particular spherical cavity, cos theta component is only effective. So, we take this component alone only. So, therefore, dE4 is equal to dQ cos theta by 4 pi epsilon naught r squared. We have already know the value of dQ. Substitute the values, then find the value of dE4. But we are in need of the electric field intensity E4 only. So, in order to doing this, we have to integrate the equation with respect to 0 to pi. So, E4 is equal to integral 0 to pi dE4. After performing integrations, we have to assume some small steps. Let us consider x is equal to cos theta. So, therefore, dx becomes minus sin theta d theta. Substitute these values in the previous integral, and after simplification, we get E4 is equal to P by 3 epsilon naught. So, we have find out all the electric field components E1, E2, E3 and E4. Now, it's the time to find the local field. The local field is also represented as Lorentz field. So, therefore, EI is equal to the sum of all the four components E1 plus E2 plus E3 plus E4. Substitute all the field. Then, after making simplification, we get the local field. EI is equal to E plus P by 3 epsilon naught. So, this is the local field or internal field, and this field occurs when we apply electric field to the dielectric material. Particularly, the dielectric material is placed inside the plates of parallel plate capacitor. EI is equal to E plus P by 3 epsilon naught. Here EI is the local field or internal field, and E is the field which we apply to that material, and P is the polarization vector, and epsilon naught is nothing but the permittivity of the free space. Next, let me explain Clausis Mosotti relation. Yes, in order to find the Clausis Mosotti relation, once again we consider the dielectric material. We are totally having 4 types of polarizations. Among that 4 types of polarizations, we already saw that space touch polarization is a very slowest process. Moreover, we consider the material having some cubic structure. So therefore, its ionic and orientational polarizability is also 0. The total polarization is the combination of 4 parts: electronic, ionic, orientational and space charge. Here our considered material belongs to cubic structure. Here we consider that the orientational as well as ionic polarization leads to 0. It can be written like this: alpha I is equal to alpha O is equal to 0. Alpha I is nothing but ionic polarizability and alpha O is nothing but orientational polarizability. Next, we know the polarization vector. Yes, polarization is nothing but the dipole moment per unit volume. The polarization vector for the dielectric material can be written as P is equal to N into mu. Okay, here mu is the dielectric moment. P is equal to N alpha E into EI, because this mu is proportional to the applied field. Here this mu is proportional to the applied field. So mu is replaced as alpha E into EI. Here alpha E is the electronic polarizability, because electronic polarization occurs at all frequency ranges. The other 3 polarization becomes 0. So P is equal to N alpha E into EI. Here EI is the local field. Local field value, we know that EI is equal to E plus P by 3 epsilon naught. Substitute the local field value, we get P is equal to N alpha E into E plus P by 3 epsilon naught. Then inner multiplication, after getting inner multiplications and some simplification process, find out the value of polarization vector. This polarization vector becomes P is equal to N alpha E into E divided by 1 minus N alpha E by 3 epsilon naught. We have to also calculate the polarization vector from the basic definitions. So from the basic definition, the value of polarization vector is P is equal to epsilon naught E into epsilon r minus 1. Here epsilon r is nothing but relative permittivity of the material. So take this as equation number 2. Already we derived the polarization vector values. Compare these two polarization vectors and making simplifications. After simplification steps, we get N alpha E by 3 epsilon naught is equal to 1 by 1 plus 3 by epsilon r minus 1. Taking LCM, then finally we get N alpha E by 3 epsilon naught is equal to epsilon r minus 1 divided by epsilon r plus 2. So this is the Clausis Mosotti relation. Once again, I repeat, in order to find out the Clausis Mosotti relation, let us consider the dielectric material and it having some cubic structure. So therefore, its ionic polarization as well as orientational polarization is 0. So it accumulates only electronic polarization. And then after applying the formula for internal field, yes, the local field, we get the relation as N alpha E by 3 epsilon naught is equal to epsilon r minus 1 divided by epsilon r plus 2. So hence we obtained the Clausis Mosotti relation. I hope all get some details behind dielectric materials, polarization, then local field as well as Clausis Mosotti relation. Thank you.